In this video, I'd like to talk about calculating means, standard deviations, standard errors, t-tests, effect size, just various ways to describe simple data. We're going to start. This is our data set, which we have 10-year-olds with extreme myopia, emmetrope, hyperope, or extreme hyperopia. They're actually they are classified based on after they've been in a study for about 8 years, and this is when they are 10 years old. Varies from 2 to 4 years being in the study. So we can see what's happening with their spherical equivalence and relative peripheral refraction. Now, before we get started, I would like to I'm going to put the means and standard deviation, some of this stuff up here, and we're going to want, I'd say, at least 4 rows blank. We have 2 now. So the way you can insert some rows is you can just copy down. You make the arrow come out on the left there, and we've highlighted 2 rows, and we right click and insert. And then we get 4 rows. And we're going to put in the mean, the standard deviation, the number of subjects, and the standard error. All right, so how do we calculate a mean? And let's do it for this this first column here, extreme myopes. And remember, again, every function you start with an equal sign. Now, I'd like to be able to type mean, but unfortunately, for some reason, a long time ago, Excel used the word average, and they have used that ever since. So I'm going to put in the word average. I'm going to hit a tab, and I'm going to click in row 7 here. And then I'm going to go Control Shift down arrow, and you can see that I have gone down to the bottom of the row. I'm going to close my parenthesis, and there's our mean. The mean myope, extreme myope, is 255. All right, let's look at the standard deviation. Now, there's a number of different functions for standard deviation. This one right here is the simple sample deviation, and it's a legacy function, but it's still the one I use, just easier. I mean, it saves some time. This, for example, STD EVS, it's the standard deviation of a sample, which is identical. Those two are exactly the same thing. And the STD-EV.P is the population standard deviation. The difference between these two is population is the sum of squares divided by n, the population one, and the standard deviation .s is the sum of squares deviations divided by s, and are divided by n minus 1. And let me just come up here and hit a tab. Okay, let's try that again. Equal STDEV tab. And then we'll do the same. Oh, watch it. 29. Oops, almost caught me. Got to come up to the top here. Control Shift down arrow, and then close our parenthesis, and we get this. So the formula for the standard deviation, what that function does is it is the square root of, let's see how to do this. It's kind of hard to do this in Excel like that. I don't think I'm going to be able to do it. So just look up, it's the sum of the square deviation. So you take x minus mean of x, you take that quantity, you square it, and you add, so the sum, or take this value minus the mean, 250 minus 255, that's squared. You do that every time for all of these, 35 times, and then you divide that sum by n minus 1. You get the average, basically, of those deviations of each of these values from the mean. That's the standard deviation. And you take them all, you take the square root of that, and that gives you the standard deviation. If you don't take the standard deviation, or if you don't take the square root, you get what's called the variance. So variance is the standard deviation squared. All right. Let's look at how many people we have. We're going to do a count. We're going to come down here. I'm going to get it yet, I just know it. We're going to go down here and we're going to highlight all of those values and hit N, and there are 35 subjects. And then we want to calculate the standard error. Now, I don't believe there's actually a standard error function in this. Let's see if we come down here. ST. Nope, at least it doesn't, it's not one that starts with ST. Okay, so what we want to do is, again, we're going to do a formula. So we start with an equal sign. We're going to come up here to the standard deviation. What's the formula for the standard error? Think a minute, think a minute. Standard deviation divided by the square root of n. So standard deviation divided by the square root, that's the square root function, and n, oh man, hit it, B3. Okay. So the standard error is 0.18163. So the mean is the sum of all these divided by n. The standard deviation is the sum of the squared differences of each of these values from the mean, squared, and divided by n minus 1. And then taking the square root, and you get the standard deviation. Then n is the count of everybody, how many there are in this row, column. And then the standard error is the standard deviation divided by the square root of n. All right, now, as an exercise, I'd like you to do that for each one of these, but I'll tell you what, you don't really have to. You can either do this and get them all, or you can copy, Control C, and come over here and paste. And those are the means for the spherical equivalence and the relative peripheral refraction. We've covered all of those. Now, what do we have here? Let's just confirm that. Let's pick this one. This is the average hyperope. You can see it goes all the way down. This is the standard deviation, and it goes all the way down. Count does, because it's 35, and then we take the standard deviation, which is blue, divided by the square root of the red, this, and we get standard error. So that did that. Copied all those formulas across there. Easy peasy. Okay, now, what else shall we do? I think it would be kind of fun to see what these means look like. Now, I am going to highlight the values here and the first row of actual data, but I'm only doing that because it's easy to draw a graph that way. We're not going to keep these. We're going to switch those to the means because we want to graph our means. So I'm going to insert a bar graph, and then I am going to click on that, and I am going to move this guy up here. And now we have the means of emmetropes, myopes, or extreme myopes, emmetropes, hyperopes, and extreme hyperopes. So see how these guys are in the middle here? We don't really care for that too much. So I'm going to click on the legend, or not the legend, the axis here. So it's highlighted. See, click. And then I'm going to right click. I'm going to go down to Format Axis. I'm going to go to Labels, because these are the labels. I'm going to go to Labels. And down here, Label Position. Right now it says Next Axis, because it's sitting right next to this center axis. We're going to move it low. Now it's down there. Now it reads a little better. And oops. Let's move this. Grab the edge here. Move this over here. I'm going to bring it down below the freeze pane line. Okay, now these are diopters. Actually, we'll get rid of the chart title. We'll come up here to Chart Design, add a chart element. Go to Primary Vertical, and these are diopters. Notice it comes up here, and generally speaking, it's nice. Well, we'll get to the formatting a little bit more later. All right. Now, it'd be also nice to know let's plot that next to relative peripheral refraction. So to do that over here, we're going to come in and we are going to right click. We're going to select data, and this says series 1 right now. Let's edit this. Let's come over here and click series name, spherical equivalence, yeah. Okay, and now let's add series name relative peripheral refraction. And for the series values, we want the relative peripheral refraction names. Extreme myope, here we go, mean over here. Okay. Let's see what that looks like. Now let's add I think I'll get rid of my freeze panes. Freeze panes, unfreeze them. Now I'll move this guy up here. I'll be a lot happier. Okay. Now, let's add a legend. Chart design, add chart element, legend. Do we want to put it at the right side, the top side, the left side? I didn't want to put it on the left side. undo that. Finger twitch. Legend. Bottom. Spherical equivalence, relative peripheral refraction. So notice extreme myopes, they have this nice pattern of heading upwards. And what do the relative peripheral fractions do? If you're myopic, extreme myopic, you have a bit of a hyperopic. Or if you're myopic, extreme myopic, you have a bit of a hyperopic relative peripheral fraction. You know, we know that to control myopia, we know about this, and we try and give them some plus to bring it down here. Let's look at the myopes. A little less. Hemetropes, almost equal. Hyperopes, look at this. For hyperopes, they don't have hyperopic defocus in the periphery. They have myopic defocus in the periphery. Now, this is a hyperope. Their eye is too short. We want it to grow. What is relative peripheral refraction telling that eye? It's telling it, hey, hold on, buddy. Don't grow. Stay short. Stay out of focus. Crazy system. All right. So that's that. Let's get this out of the way. Now, some other things we want to do is we want to look at, we're going to do a t-test. And to do a t-test, the formula is x1 minus mean 1, or the mean difference, divided by the standard error of the difference. And the standard error of the difference, I don't know if I'll have any better, I'll try just typing it out, is the square root of SE1 squared, pretty unsatisfactory, SE1 squared plus SE2 squared and it's just the sum of those two. You know, when we talk about effect size down here, we're going to talk about the same difference in means divided by the average standard deviation. Here we talk about adding them up. When you're looking at that big distribution, it's wider. That distribution of hypothetical means is wider with when you're doing a t-test than it is when you're just doing a single mean distribution. So it's got two means, distribution's wider. All right, let's do a t-test. So, you know what, maybe okay, let's make this just a tad smaller. Okay, so we've got, now we're going to do, what are we going to do a difference of? Let's do the difference between emmetropes and myopes. All right, so we're going to do the mean difference is equal mean myope minus the mean emmetrope. That's the difference. The SED is the square, oops, it's down here, it equals the square root of the standard error for myopes, and squared in, or to raise to a power, use a little caret sign, it's right above the 6. C4 2 squared standard error plus this one, squared raised to 2, close quote. That's the standard error of the difference. Then the t-test is the mean difference divided by, makes me crazy, it hides it. So it's this row, which is 14 and n, so it divides by n14. There we go, see if we, that still hides it. So the t-test is minus 7.5. That means the null hypothesis is that these differences are not equal, that those two means are equal. The null hypothesis is these two means are equal, minus 0.78 plus 0.67. Because those two are the same. That's the null hypothesis. That's what we're testing. And we are minus 7.5 standard error units away from that sameness. In other words, think about how you might have heard the expression that they're normal if they're plus or minus 2. Well, standard deviations, this is kind of the same thing. You would be normal, or the null hypothesis would be true, if you were plus or minus about 2 standard errors. But you're not 2, you're minus 7. That's way, way different. So what's the p-value? So the p-value function is equal Ttest, which is t-distribution, and we need an x, which is going to be the t. We need degrees of freedom. Degrees of freedom are n1 plus n2 minus 2. And then it asks, are you doing a one-tailed or a two-tailed? We pretty much always do a two-tailed. That is part of the, it's a null hypothesis. It's chance. It can go either way. It can go to the left or right. So it's a two-tailed. We're testing the chance. And the chance can go either way. But we see that it's not chance. Oops. Now that might not have liked it because it was just too crazy. Oh! Aha! Yes. This function Ttest, does not like negative numbers. So we have to make this an absolute value. It doesn't matter with respect to the t value, but we're going to do absolute, and n15 is the t. So it's the absolute value of the t value, this blue thing here. And this is 0.000000000012. That's the p-value. Tiny, tiny, tiny p-value. So we say this is statistically significant. I'm going to come up here, go to my little home, and make that left justified. All right, now let's calculate the effect size. What is the effect size? The effect size is the difference between means, same one, difference between means, so equals the difference between means. You could also just do it again if you wanted to, subtract those two, but we're not going to do that. Divided by the average of the two standard deviations. And the average of the two standard deviations is average, and then we're myopes and emmetropes. Those two. And the effect size is minus 1.85. Now remember, again, the sign doesn't matter. It's just telling you the direction based on the direction of the subtraction. Now we might want to, just for the heck of it, kind of cut down the decimal points there. So we would come up here, and there's increased decimal points, decreased decimal points. We want to decrease them to maybe 2. This one, it's kind of a lost cause. We would go and home, and do that. Now for the p-value here, we would be more inclined, rather than to give that big number, p less than 0.001. That would be a better choice than this long scientific number. And the effect size is clinically relevant. So there you have it for the difference between the spherical equivalents for myopes versus emmetropes. The mean difference is 1.45 diopters. The t-test was minus 7.58. The p was less than 0.001. And the effect size was minus 1.85. This is a really big effect. There's a big difference between emmetropes and myopes, as you already know. But there it is in black and white statistical sense. That's it.